The lecture today is about the estimated population proportion, and population proportion is the estimation is always by using z-intervals, which means that we are going to use the central limit theorem, and because of the variable of polling is not normally distributed, the central limit theorem that we are using is the fact B, the second part of the central limit theorem, the way we outlined, and for that one we would need a large sample. So every time we do the polling to estimate population proportion, we will always need a large sample, meaning 30 or more. When you are polling something, the random variable of the polling is going to be either it's going to have two values, either 0 or 1, meaning we label that 1 for yes or a success if you like, and 0 for no or a failure if you like. So this is the random variable that we made some time ago. We called it binomial random variable, and since there are only two possible values, this is with one trial only, and we have a name for this random variable. We call that Bernoulli random variable. So this is binomial random variable with one trial, and the probability of success on any given trial is whatever the proportion of the population is. Right? If you're trying to estimate the number of smokers in the population, you will get a sample. In that sample, you're going to get something, and that's going to be your sample proportion. And I don't know what that might be, but every individual in the sample has a chance of being a smoker the way that the proportion of population is. So if there is a 30% of the population that smokes, then everybody in your sample has a 30% chance of being a smoker, right? So that's the kind of thing we have. So you're going to have a binomial random variable with one trial. So that person is either going to be 0 or 1, yes for a smoker or no, depending whatever you consider, and the 30% for the probability of success, right? Binomial random variable with one trial. We have a name for that. We call that Bernoulli. So for example, I could try to figure out how many of the students in Suffolk County Community College think that math is an easy subject. What proportion thinks that math is an easy subject? What can I do? I could collect a sample from my students and ask them the same question, and I would probably get some answers there. And this is like a sample of 30 students in which I get first one thinks it's not an easy subject, the second one the same, the third one the same, the fourth one thinks it's an easy subject, and on you go. And I got a total of 10 of them, 10 ones out of 30 0 and ones, right? So it's 10 out of 30, or 1/3 of the people in this sample think that math is an easy subject. So all in all, basically, the formula to calculate the proportion of the sample, so the proportion of the sample, the mean of the sample, you sum all of these numbers and you get 10. 0 don't really count, but you're summing only once. And if you sum in all of them, you get, just like summing once. So you get 10 on the top. On the bottom, you have how many in your sample? 30. So it's 10 out of 30. Or 33%, if you like, to write that as a percentage. Now this is your typical sample mean, okay? The random variable of polling is a Bernoulli random variable. It's 0, 1. So you have it in one instance is 0, another instance 0, another instance 0, another instance 1, and on you go. Okay? So that's the Bernoulli random variable. So what do we know from a central limit theorem? For central limit theorem, first of all, we know the Bernoulli random variable has the mean P and the variance PQ. The Q is complementary to the P, right? P 30%, Q is 70%. P 40%, Q is 60%. Now you can check this back in the lecture of binomial random variable. We wrote that down. The Bernoulli random variable has this as an expectation. This is a mean of Bernoulli random variable. and this is the variance of Bernoulli random variable. So we know from a central limit theorem that if x has this as a mean and this is a variance, then x bar is the sample mean, the sample proportion as we call it here, and that will have the mean the same as the original variable as an x, so that should be p, and the variance is going to be the n times smaller. N is the sample size. So this is now important because now we have the normal random variable in the game. So when we are looking for the confidence interval for the sample mean, you do remember that we have that x bar, give or take, and then we have, that's a z interval, right? The z critical value, lowercase z, I made it too big here. I can make a little smaller, z critical value. And z critical value will have some confidence associated with it. And so we say label half a significance here. Labels are not that much important, but you do have to remember the actual values, right? Whatever confidence you're going to use. And then we multiply that with the standard deviation of the sample mean. Okay? Or we call it standard error of the mean. Now that would be the radical of the variance of the mean. So if you take the variance in the case of polling, this in the case of the mean proportion, then you're gonna have to you will have to take a radical of this fraction here. So that would go here. Just a different label. It's the same story. This is standard deviation of the sample mean. Only in case of proportion we are labeling that differently. So we are going to replace this with this guy. And the sample mean in our case is a sample proportion. So the x bar, again different labeling. We would use a p bar, but we don't really use bar, we use hat, right? Okay, and now we have a formula for the z interval to estimate population proportion. But there is a little problem here. We are estimating p, which is a population proportion. And yet the formula requires for us to have p and q in it. So that's not possible for us to find out, because if I would know what a p is, I would have no need to estimate p. I do have a sample parameters though. P hat and q hat, what I got from a sample. And now you remember, I mentioned that time ago that if you were missing population standard deviation, you can use the sample standard deviation. And that's another limit theorem. In this particular case, if you're missing PQ, which will be the variance, theoretical variance, you can use a sample variance P hat, Q hat. And that P hat, Q hat divided with N is approximately close to PQ divided with N. I'm stating another limit theorem. So theoretically, I need to have here P and Q, but I'm estimating P, so I don't know what the P and Q are. So I'm replacing them with the sample parameters. If the sample size is large, there will be no big mistake here. Okay, I'm going to show you at the end also, if you really want to be very conservative, you can just simply use 0.5 and 0.5 here. But then you would have rather imprecise estimate. In any case, this is the formula for the Z confidence interval when you are estimating population proportion. Okay, so this is the formula right here. Again, I have it right here, which is the same thing I have here. It's much nicer here, of course. Okay, so here is an example. In this example, we are having a poll done prior to the election in October with 474 likely voters nationwide. And we were asking whether they support President Trump for re-election or not. So 213 of them say they would support him. So that is roughly 45%, 213 out of 474. Now, if I want to use this poll to estimate what is the population proportion supporting president for re-election, now in October, of course, elections are already over, I would now use my poll data and I would come up with the estimate for the population proportion. Okay, so how do you do that? Well, I'm going to just simply use this formula here. I have all of the numbers that I need. P hat from a sample. Everything in the formula that I need, I already have. It's roughly 45%. If you want to be a little more precise, you can say 213 out of 474. Then you have a Q hat, which is the complementary probability, which will be 55%. Or again, if you want to be precise, you can, since I'm precise here, really, I have to just simply say equal. So the Q hat is how many in the sample are not supporting him. So that would be, I guess, 261 out of 474. Okay, roughly 55%. We also know the N, of course, the sample size. Obviously, I mentioned that already a couple of times. Is 474. Check. Large. Sample is large, of course, because we need to use the central limit theorem. Without large sample, we cannot do any estimate here. And then Z, critical value, in our case is the label would be half of significance, so that will be 2.5% for a label. That is really not that important. The critical value itself is important to know, and that we have approximately 1.96. This is one of those numbers that you need to remember, right? Critical value for 95% confidence. There is confidence of Z random variable anywhere between negative 1.96 up to positive 1.96. There will be 95% chance that Z could show up in that interval. Okay, everything is here. The rest is just a simple calculation. So I'm using the formula P hat 213 over 474, or approximately 45%. Every percentage ought to be used in calculation as a decimal number, right? I keep on reminding you about that. Give or take the critical value, Z alpha half, in this case Z alpha half is 0.025, 2.5%. Half of significance, 1.96. I'm writing that down here. And I have the radical of the P hat Q hat divided with N. So I have a P hat, so this is approximately 45%. So I'm using that number rather than to have multiple fractions, but you might as well use your calculator for all of that. And this one, of course, is 55% also as decimal. So I'm going to put it in the formula, and I'm dividing with the n, which is 474. And the result is, for the maximum error of the estimate, or colloquially we call that margin of error, I'm getting 4.5% approximately. So our estimate for support for president in October was 45%, give or take 4.5%, which means if we want to state this as an interval, we are going to subtract with minus here. That will be the lower bound, and if you do that, you're going to get the 40.5%, 0.405, and the upper end of the interval would be by adding 4.5% to 45%. So that's the 495. So from our statistical point of view, he is going to lose election, right, in October, which actually is what happened. But in this story here, we 95% confidence, right, which means that there is still 5% chance that the population support for him is not in this interval, but there is a 95% chance it is. Maximum error of the estimate, or the margin of error, is 4.5%. It's a sort of large. So the question is, can we make this a little better? Can we make a better estimate? Yeah, we can decrease the confidence, which is really not a good idea, or increase the sample size. Decreasing the confidence will give us lower margin of error, but what we really want to do is actually rather increase the sample size, so we can get better estimate if we do that without trading confidence for it. Okay. Here's another example. If you are keep on shopping in the same supermarket and same grocery store chain, you would be considered to be a loyal customer, and you might even have a card or things like that, which entitles you to some sort of a discount. They want to give you that, so they, for reasons very simple, they want to collect information, what are you buying, so that they can stock the stores, and it's more efficient way for them to operate. Okay, so Food Marketing Institute, which is the association of all of those grocery store chains, was doing polling here, and they poll 730 shoppers for the loyalty, and they define loyalty by being a shopper that goes to the same store in a 1 year period, which is probably what happened to the most of the people, right? You keep on going over and over to the same store unless you find something cheaper or closer, things like that. So they find out that 628 out of 730 of those they poll would be yes, meaning loyal, and there was 102 apparently that switched their loyalty, went to another grocery store during that 1 year period. So obviously they would like to know what is the percentage of loyalty, what is the percentage of loyal customer, and we're gonna do the 90% confidence here, 90% confidence interval. So we already know we are polling proportion of loyal customers, so we are going to use Z interval. We have the formula for that Z interval. That's the formula here, and I have the numbers I need. I have the p hat, the proportion of loyalty in the sample, which is 628 out of 730. Then obviously the Q hat will be the proportion of those that are disloyal, if you want to call it that way, would be apparently 102 out of 730. That turns out to be approximately 14%, which means that the p hat is approximately 86%. It's nice to have that in terms of decimal number because it's going to be easier to calculate with. But then, of course, you're losing some precision because the fraction is not exactly the same as this decimal number. And I do have n. Of course, n is obviously 730. The size of the sample. Again, check. This is big. It has to be, because again, we are using central limit theorem, fact B, so we need to have a large sample. The sample is quite large here, okay? So now I have the only remaining thing in this formula that we did not state yet is the critical value. The critical value, of course, is related to the confidence of 90%, and the critical value for that would be 1.645. So we have p hat from the formula, again, using the formula. I don't want to scroll back and forth all the time. P hat, give or take, the critical value in our case is, let's just write in general case, it's alpha half, significance half, time, that's just a subscript label. And then we have a p hat inside, radical, q hat, both divided with n sample size. So that's what we have here. 0.86 is p hat, critical value, radical, p hat 86%, then we got that out of here, dividing 628 with 730. Q hat, the complementary to 86 is 14%, you don't have to divide again if you have that already calculated. Down there is n sample size. Turns out to be that this is, after you calculate this nicely, by using calculator, I guess, would be 2% only. So, what can we say? That proportion of people that are loyal to the same supermarket in 1 year period is anything between 84%, that is when you subtract 2% from 86%, that's a minus here in the formula, 86 minus 2, and all the way up to perhaps 88%. This is by adding 2% to 86%. So the proportion of the customers that are loyal to the same supermarket over 1 year period is anywhere between 84 and 88%. Or you can say 86% give or take 2%. The maximum error of the estimate is 2%. You can use either of the terms. How sure are we in this estimate? This is an extremely good estimate. The margin of error is only 2%. We are 90% confident that this is good estimate. All right? Now, for the purpose of marketing, I guess this would be okay confidence. Maybe you would want a little more, maybe 95%. You can recalculate this again. Okay. But well, I'm happy with the estimate here in this example 2. I'm not all that happy in the example 1 because there we have a margin of error of 4.5%, and it's kind of like interval is rather wild. I mean, from 40.5% to 49.5%. So this is not very precise, even though the sample is fairly large, 474. So if you want to improve the estimate, as in getting margin of error smaller, then you would say that you're not going to allow margin of error to be bigger than some kind of error tolerance that you want to have, like error tolerance, something that you, let's say 2%. in the first example, I have 4.5% for a margin of error. So let's say I don't want to have 4.5% margin of error. I want to have much smaller. I don't want to have it bigger than 2%. Then 2% is the error tolerance. So the error tolerance, the margin of error, a requirement is that it's not going to exceed the error tolerance. The error tolerance is 2%. Okay, now you have to work this out. So you have to find equality for a sample size. Okay, what you need to do is to divide with z alpha half, so you get the E divided with the z alpha halves. I'm doing a little algebra here. If you're not interested in doing this algebra, tune out and tune in when I end up with the formula. This is going to be bigger or equal, then I have this piece here, radical. Well, I can immediately square everything, so get rid of radical. Square here. On the other side, I had p hat q hat over n, and I guess I need to flip it up now, upside down, this to get the n on the top. So, and then I have to flip this too, and finally, so I need, the next step is flipping everything, and I guess I need to flip it up. So, and then I have to flip this too, and finally, so I need, the next step is flipping everything. Flip the fraction. It's actually a square, but you can, you square numerator and denominator, so you're basically flipping the fraction. Okay. You need to flip the sign of inequality. From here, bigger or equal, now it's smaller than equal. And I have n divided with p hat q hat. I flip that fraction too. Okay, now I just need to multiply with these two guys to get n alone. And I got this, n bigger or equal, and now I'm multiplying with these guys, so I have a p hat q hat and the square, the same square I had before. Error tolerance in denominator. All right. Now it's nicer to have the n on the left side, right? You can get used to when you solve for variable. Variable is on the left side. It's bigger or equal than this thing here. Okay. So if we want to improve this estimate for the proportion of support for Donald Trump in that poll, we definitely need to increase the sample size. And how big of a sample size that's going to be? Well, according to this formula, if you don't want the margin of error to be bigger than 2%, then your error tolerance is 2%. You want to keep the same confidence, so the z-critical value is still 1.96 because you want to keep the confidence on 95%, right? You can also improve your estimate if you decrease your confidence, but that's really not a good idea, right? You get the margin of error smaller, but you're also losing confidence. Confidence is also a lower percentage, but you don't want to do that. So we're going to keep the confidence. And the p hat and q hat is what? P hat and q hat is from an eventual sample, but we only have a preliminary sample, so we can use preliminary sample. And in preliminary sample of 474, we have 45% for p hat and 55% for q hat. Okay, so I just need to now calculate what this product is. So you get to divide this guy with this guy, make a square, multiply with 0.55, and multiply one more time with 0.45. I ended up with something like 2,377. And again, you always go up. If it's a decimal number, you're always rounding up, right? Well, if I'm doing this poll, I'd probably say, let's go for 2,400, because to avoid any coincidental errors, when you're using exact numbers. So you need at least 2,377, but you'll be safe if you go for 2,400. You have to get this many voters in your sample, this many people you're polling in your sample, and you only have right now 474. So basically 474. So basically you need to add another 1,903 to get to this number. It's a lot more work. You're going to get a better estimate, of course. According to what we just calculated, the estimate that you're going to get will have a margin of error that will be no more than 2%. So you will not get a margin of error like a 4.5% like we have in the original estimate, but something less than 2%. How good is that going to be? I don't know. All right, but you have to put up a lot more work. So again, you can see the improving the estimate in the polling situation would imply a lot more work. Okay, now sometimes you don't have a preliminary sample. Let's say you right from the get-go you're trying to figure out how big of a sample you need, and you only have the idea what confidence you want and what kind of error tolerance you're going to allow. Now in that case you don't have p hat and q hat. If you don't have p hat and q hat, you just started, you didn't poll anything. What are you going to use? You're going to use 0.5 and 0.5 for p hat and q hat. Why? Because according to this formula, n has to be bigger than that, than this stuff here, right? The n has to be bigger or equal than this, what is on the right side. So I have to tell you that 0.5 times 0.5 is always bigger than a product of p and q, no matter what p and q are. Okay? Why? This is 0.25. When you multiply 5 and 5, you get 25, and of course you have two decimals. Take anything else, like maybe 70% and 30%. That would be 0.7 and 0.3. That is going to be 0.21. And you can see that this is less than 0.25. You can try something else like 0.6 and 0.4. That will be 60% and 40%. And again, you're going to get 0.24, which is again less than 0.25. You can try any other P and Q, and you will always get less than 0.25. The only time you're going to get 0.25 if you take 50-50. That's an interesting thing to know. So if you are going to go above 50-50, you will go above any other product of P and Q. That's an interesting thing to know. So if you don't have a preliminary sample and you didn't do that work, you can still find out how big of a sample you need by just simply using this formula. You will know what confidence you want, you will know what error tolerance you're going to allow, and you can use here 0.5, 0.5. Okay, and then you're just going to do the same calculation. So instead of 0.45, 0.55, you would have 0.5, 0.5. And of course, you're going to have a bigger n. What's going to happen here, I can actually use a calculator to find it out. So if I instead of 0.45 and 0.55 use 0.5, 0.5, I'm going to have is 0.5 squared, right? 0.5 times 0.5. And then I would multiply that with the what says in this formula 1.96 divided with 0.02, and even that I need to put it on a square, right? I have to use a square, and I have 2,401. Not that much. Okay, so without preliminary sample, I still know I need to have a little more than 2,400 people in my poll to be able to claim population proportion estimate with the margin of error, or give or take, less than 2%. That would happen. Okay. All right. Another thing I want to show you, so this is about the sample size. Another thing I want to show you is how to calculate this by using your calculator. This is really not that difficult to calculate by using formula. Formula is relatively simple. But if you use a calculator, you can do the same calculation. So the calculator will do the calculation, of course. You're going to just use a calculator, right? So you have to go for statistics. The option of tests ought to be used, and you have to go to the A option, says 1 proportion Z interval. You got to remember that. So you are doing a Z interval for the population proportion. It's only one proportion, so it could be actually two different things in population that you're polling. But if it's only one proportion and it's a Z interval, this is to be used. And then you click on that. It will ask you, so in this example number 1, how many successes you have in your polling, and in polling we had 213. The people that were telling us that they will support the Trump presidency, and then you have the how many you have in your sample, 474. The confidence level we wanted in this particular case 95%. So it's typical polling confidence level you use. If nobody ever says what a confidence level is, that is always 95%. All of those polls that you ever heard of, Gallup poll, Zogby polls, CNN poll, MSNBC polls, Wall Street Journal polls, they're always with 95% confidence. And then you calculate, and I got the same thing, pretty much what I have here. I ended up with the 45%, give or take 4.5% in the interval. That I have is 14.5%, 49.5%. This is what you see here. A little more precise, because if I want to round this to 3 decimals, I have 405, which is the same thing I have here, and 494. Okay, so a little different in the third decimal. Okay, this is a by the way, your calculator will not tell you, your calculator here is not telling you what is the margin of error, but you should know that when you have a confidence interval, in the middle of that interval is your point estimate, which is in this particular case p hat, right? And at the end of that interval are you adding or subtracting, and that's a margin of error. So this is a margin of error, or the maximum error of the estimate, that's how we call it. And so is this. The same thing here. So you got a margin of error, and then you can just simply subtract the end of the interval minus the p hat, or a p hat minus the beginning of the interval. So in our case here, when I get this thing, what I need to do is to subtract this number minus this number. So this is the upper end of the interval minus the point estimate. Or if you like, point estimate minus the lower end of the interval. So this minus this. Or this minus this and divide by 2, right? This minus this is the double margin of error, so you have to divide by 2. So what I have here is point, oh, now I lost it, right. I cannot remember. It was 0.4 49419, something like that, right? Minus, okay. I will go back again to do the same test again, just to make sure. That I get this proper calculation. All right. Third time. One, two, three. Okay. So I'm gonna have to use my computer calculator here. So because if I start calculating here, I'm gonna lose the screen. So 0.49415 minus, yeah, I made a mistake. Such a simple thing to do, right? And I'm not able to do it. Okay, let's try again. 0.49415 minus, and I have p hat there. 0.493670886. Wow. Okay, and I get 4.5% again. I mean, if you do rounding on the third decimal, end up with a 4.5%, right? That's how you're gonna find the margin of error if you use your calculator, because your calculator will not tell you margin of error. It will give you the interval on the top. It will tell you what the point estimate is. That's it. Okay. So let's do the same thing again for this Food Marketing Institute or shopping loyalty, proportion of loyal customers. Again, the menu option for tests, the A1 proportion Z interval. This time we have the number of successes, the number of yes in our polling was 628. And then we have the total number of polls, total the size of the sample, 730. The confidence level this time is 90%, 0.90 or 0.9, and calculate again. And again, okay, this time I got something much closer to what I have here. Not much closer, but it looks like I have pretty much the same I have here. So I was concluding interval is 84 to 88%. That's what I got here. So this is approximately 84%, right? 83.9% of 84% if you go with the nearest percent. And this is obviously 88% in terms of the nearest percent. And also I had the point estimate, which is 86%. We calculate that easily from dividing 628 with 730 anyway. Right? It's fairly easy to use that. Okay, the sample size is not on your calculator, too bad. Meaning you will have to actually use this formula. How to get a sample size. And again, you will know what error tolerance you want. You will know what confidence you want. And in case you have preliminary sample, you're going to have p hat and q hat. If you don't have a preliminary sample, you can use 0.5, 0.5. And then when you calculate that, the formula will tell you how big of a sample you will need to collect to get that desired precision, or how small of a margin of error you want to have, right? Precision is all about margin of error. You're going to have a point estimate, which is just a number, and then it's give or take. So that is the margin of error that you can limit by using the error tolerance to whatever the percentage you prefer to limit that to. Okay, so this is the story we have for this estimating of proportion. It's not a difficult thing. It's something relatively easy to understand. I think it is, once you understand of course, the estimation of mean. And this concludes our story for estimation completely. So now we have the estimating population mean by using Z interval, estimating population mean by using T interval, and estimating population proportion, of course, by using Z interval. Right? These three things are all included in the homework 13 about the estimation. We have a homework 10, 11, and 12, which is about non-random variable central limit theorem. And one more is coming, the homework 15 is going to be about the hypothesis testing, and that homework is not yet assigned. These topics, or you can say these homeworks, 10, 11, 12, 13, and 14. 14 is the last homework you're going to get. And these last two homeworks are actually extra credit homework. These 5 homeworks are with the topics that you're going to be tested on the final exam. So you need to work on those homeworks, even though the last 2 homeworks are extra credit homework. Of course, if you want extra credit, this is what you're going to work on. If you are not interested in working that much on the homework, but at least you have to work on those homework for the final exam. So one way or the other, they're not really extra credit in terms of what you need to learn. Okay? So that's my story about the estimation. So there's one more topic we're going to be studying, and it's going to be hypothesis testing. We're going to spend at least a week on that before the final. Okay? I'm going to stop the video.